This is the 7th lecture of my series on motion in a central force field. In fact, this is more of a continuation of my last lecture, the 6th one, which was sort of truncated because of technical difficulties. Let me remind you that there we were essentially talking about motion specifically in the Kepler potential U of r equals minus capital K over r, where capital K is a constant which, when positive, indicates that the force is attractive, and when negative, it indicates that the force is repulsive. The magnitude of the central force that you calculate from this U of r turns out to be minus K over r square, the famous inverse square law. Now, what we had already shown in earlier lectures is that for this specific kind of potential, the orbits are all closed and they are basically conic sections and are described by the equation given by r equals r0 over 1 plus e cosine theta, where r0 and e are constants which are related to the initial conditions through the conserved quantities small l and capital E, the magnitude of the angular momentum and the energy respectively. R0 is given by L square over mu k, and the square of the eccentricity E square, is given by 1 plus twice L square over mu k square times capital E. Now this shows that when capital E, the total energy, is negative, which by the way is possible only for an attractive potential where capital K is positive, you end up with bound orbits for which the eccentricity is less than 1. So we have elliptical orbits, or in special cases we can have circular orbits. And for these orbits, the maximum and the minimum distance from the center of the force turn out to be r0 over 1 minus e and r0 over 1 plus e respectively. Now, the sum of these two distances divided by 2, that is the arithmetic mean, is the semi-major axis of the ellipse, while the semi-minor axis is given by the geometric mean of these two numbers, the pericentron and the apocentron distances. We can also rewrite the conserved quantities in terms of the orbital parameters. Total energy is given by minus k over r max plus r min, which is the same as minus k over twice a. So it is a semi-major axis of the ellipse which solely determines the energy of the orbit. On the other hand, the angular momentum, or rather its magnitude, is given by square root of twice mu k r max r min by r max plus r min, and using the expressions for the semi-major and semi-minor axis, we can show that this is actually root over mu k over a times b. And using these results, we had given a geometrical proof in the last lecture of Kepler's third law, that square of the time period of an elliptical orbit is given by 4 pi square mu by k times a cube. That is, the square of the time period is proportional to the cube of the semi-major axis. This, of course, is Kepler's celebrated third law, which he discovered through meticulous observations done on the planets.
From the planets, let us come closer to home. Another place where these equations are of immense importance is in the study of satellites which go around the Earth. Now this is a huge topic in itself, and entire books can be, and indeed has been written on this topic. So I can only scratch the surface of this huge topic. Let us begin with a very simple situation. Just the basics. Let us consider a satellite orbiting the Earth, and the perigee height, the closest height from the Earth, we are calling HP. So this distance from the surface of the Earth to the perigee, this is HP, and the apogee height similarly is HA. Now, as is the case for all satellites, we can safely assume that the mass of the satellite is very much smaller than the mass of the Earth, so that the reduced mass small mu here is almost the mass of the satellite m. Now, From the geometry of this ellipse, it's pretty easy to see that the major axis, or double the semi-major axis twice a, which is the distance from the perigee to the apogee, is hp plus ha with an added diameter of the earth inserted in between. So it's hp plus twice re plus ha, or the semi-major axis works out to be simply the average of the heights of the perigee and the apogee added to the radius of the earth. Another important parameter describing the orbit is, of course, eccentricity. And that's also pretty easy to figure out from these heights given. The eccentricity, of course, as we have already seen, is Rmax minus Rmin over Rmax plus Rmin. The Rmax, the largest distance which the satellite encounters in its orbit from the center of the Earth, is simply HA, the apogee height, plus the radius of the Earth. And the minimum distance is HP, the perigee height, plus RE. So the numerator simply becomes HA minus HP, whereas the denominator, this sum, is nothing but twice A. So using HA and HP, we can easily calculate what the eccentricity of the orbit is supposed to be. Now, the important issue is how much energy would you require to launch such a satellite from the surface of the Earth. Now, once the satellite is in such an orbit, we have already seen that the energy is given by minus k, the Kepler constant, over twice a. So, since in our problem the Kepler constant is simply g times mass of the Earth times the mass of the satellite, you end up with minus g MEM by hp plus ha plus twice re, or by using the acceleration due to gravity at the surface of the Earth as a parameter, you can rewrite this quantity up here as mg re square and obtain an equivalent formula. Now, this is the energy of the satellite once it's in orbit, but at launch the satellite is at the surface of the Earth. So the energy at launch is simply given by minus g MEM by re, or simply minus k over re. Difference of these two is the amount of energy you would need to put the satellite in orbit, discounting, of course, all other effects like the effects of atmospheric friction and stuff like that. Ignoring those effects is actually not a very bad approximation. Anyway, the energy that you need to put the satellite in orbit is simply the difference between minus k by 2a and minus k by re, which can be rewritten in this form, k into twice a minus re by twice a re. Or in terms of the perigee and apogee heights, you can rewrite this as k into hp plus ha, and this factor here is simply twice small a times re. Another form which actually is more useful perhaps is simply this expression rewritten as k into 1 over re minus 1 over 2a, which shows that the larger the semi-major axis of the orbit is, the more energy you need to launch the satellite.
Also, as is obvious from Kepler's second law, the satellite reaches its largest speed at perigee and smallest speed is attained at apogee. And you can easily calculate these speeds using the result that mu times Vmax times Rmin, these are, of course, perigee distances and perigee speeds multiplied together, has to be the same as mu Vmin Rmax. Once again, Vmin is the minimum velocity, but that's obtained at the maximum distance. Apogee velocity and apogee distance. These products are, of course, equal to the magnitude of the angular momentum small l, which we had already seen is root over twice mu k Rmax Rmin by Rmax plus Rmin. Now, this immediately tells us that Vmax and Vmin both can be written in a very similar fashion. They are both given by a prefactor of twice k divided by mu times Rmax plus Rmin, or root over k over mu times a, which has to be multiplied by square root of Rmax by Rmin for Vmax and square root of Rmin by Rmax for Vmin. Now, let me point out that this expression that we are given for the total energy required to launch an orbit is bound to be an underestimate. Of course, as we had already noted before, you would need extra energy to overcome things like friction of the atmosphere. But there is also a reason why even if we were to ignore things like air resistance, this expression for the energy cannot give you the full picture. The point is, you cannot just hope to launch a satellite from a given point on the Earth and expect it to miraculously go into the orbit that you finally want it to go into. If you were to say, launch a satellite from this point on the surface of the Earth with a speed which is less than the speed required to send it into unbounded orbit, it is going to go into an elliptical orbit with the center of the Earth as its center. Now, such an orbit will obviously intersect the Earth's surface once again in a symmetrically placed point. In other words, the satellite would crash back onto the Earth. Now, this happens to be exactly the way in which ballistic missiles behave. But if you want to send your satellite not back into the Earth, but into, say, an orbit like this, what you will have to do is where your launched orbit intersects your desired orbit, you will have to change the speed of the satellite by using thruster rockets which are carried by the satellite itself. Now note that any such change in speed actually requires the expenditure of quite a lot of fuel. And all this has to be designed carefully when you're thinking of launching a satellite. To send a satellite to, say, the circular orbit, you will have to do precise calculations about how much speed you would have to change, in what direction, and not only would you have to ensure that you have sufficient control over the rockets mounted on the satellite. To enable this to be done, you would also have to make sure that the satellite is carrying enough fuel to do this. And extra fuel makes the launch vehicle heavier, requiring it to actually expend more energy while being launched and therefore having to carry more fuel. So all this has to be calculated with a very high degree of precision. Let me point out that here we have made an assumption that the rocket actually produces an impulse. It burns very, very hard but for a very short interval so that the satellite doesn't change its position while it changes its velocity. Now, that such impulsive thrust makes calculations a lot easier. However, in a real life scenario, you might even have to consider situations where the rocket is burning for a much longer time, maybe in several stages, and the corresponding calculation of the final trajectory will be quite complicated. We will not go into those details here, but let me just illustrate the kind of calculation we would still have to do even in the simplest case. Once the rocket has burned out, suppose you have a situation like this. You get a bunch of initial conditions for the satellite. This is, of course, after the rocket burn, so the satellite is once again under the inverse square force law only. At this point, let its distance from the center of the Earth be capital R0. I would have loved to call this small r0, but we have already used small r0 for another parameter, the parameter that's in the equation for the conic section. So we have to live with capital R0. Let the speed of the satellite at that instant be V0 and the heading angle be beta 0. Now this heading angle is the angle which the velocity of the satellite at any given instant makes with the line which is tangent to the radius vector. So basically, this is the radial direction measured from the center of the Earth as the origin. This is the cross-radial direction. And beta 0 is the angle which the velocity makes with the cross-radial direction. Our task right now is, given these three measured quantities, capital R0, V0 and beta 0, distance, speed and heading angle respectively, determining the subsequent orbit of the satellite. Assuming, of course, that the satellite from that point on moves only under the action of the inverse square gravitational force of the Earth. Now, in order to figure out how the satellite is going to move, we need to make use of the equation r equals r0 over 1 plus cosine theta. But there, the angle theta is measured from the periaxial line, the line joining the center of the force to the perigee. At this point, we do not really know where the perigee is, so our job would also be to locate this periaxial line. So this angle theta 0, which our current position vector makes with the periaxial line, is also something we need to figure out. So now, let's start with the equation that we mentioned right now, r equals r0 over 1 plus e cosine theta, where r0 we know is L square over mu k, and what we are going to do is rewrite this to write L as root over mu k r0. Note that L at any given instant is also equal to mu r squared theta dot. This quantity, of course, is the conserved quantity, which also tells us that the aerial velocity is a constant. Kepler's second law. Anyway, coming back to this current issue, we need to actually determine a formula for the speed of the particle. Rather, the two components of its velocity, the radial component and the cross-radial component. The cross-radial component is particularly simple. It's given by r theta dot, and that, of course, works out to be L over mu times r. Or, if you make use of this expression for L, it becomes root over k over mu r0 into 1 over r. Now, the radial component of the velocity is r dot, and so if I differentiate this expression with respect to time, what I get is minus r0 over 1 plus e cosine theta whole square into minus e sine theta theta dot. So this is the final expression. But this can be simplified considerably by realizing that this quantity, apart from a factor of r0, is just r square. So you can rewrite this as 1 over r0 e sine theta into r square theta dot. And since r square theta dot is simply L over mu, we can rewrite this as root over k by mu r0. That is, you are dividing this quantity L by mu r0 to end up here times e sine theta. Now, this is the background that we need to put in our initial conditions. Once we put in the initial conditions, we get capital R0 is nothing but the small r0 over 1 plus e cosine theta 0. Note that e, r0 and theta 0, all of these are unknowns. Capital R0, of course, is a known quantity in our calculation. So first of all, what we can do is try to get rid of as many of the unknowns as possible. In order to do that, let me just first write this formula in this particular form. E cosine theta 0 is small r0 divided by capital R0 minus 1. Now, the other initial condition, the cross-radial component of the initial velocity v theta, is nothing but v0 times cosine beta 0. Note v0 is the speed in this direction. Beta 0 is the angle which the velocity makes with the cross-radial direction. So the cross-radial component, of course, is v0 cosine beta 0. And the radial component is v0 sine beta 0. Now v0 cosine beta 0 is nothing but the value of r theta dot at this initial condition, or L over mu r at this initial condition, which after we put in all of this works out to be minus square root of k r0 by mu into 1 over capital R0. This same expression with small r being replaced by capital R0. And what about the radial component? The radial component is simply v0 sine beta 0 is equal to r dot at t equal to 0. And once you take a look at this formula and put in the initial values there, you get root over k by mu r0 e sine theta 0. Now, we can rewrite these equations to advantage. This equation, for example, simply gives us a value of r0 as mu over k times v0 r0 cosine beta 0 whole square. Now, this expression can be rewritten for e sine theta 0, and once you use the value of r0 here, this becomes mu v0 square r0 over k cosine beta 0 times sine beta 0. Finally, e cosine theta 0, small r0 by capital R0 minus 1, simply works out with this expression. Mu over k v0 square r0 cosine square beta 0 minus 1. Our small r0 square was simply mu over k v0 square capital R0 square cosine square beta 0. You have just divided that by r0. What is important to note is in each of these three equations, you have one dimensionless parameter which is being used throughout, which is nothing but this quantity, mu v0 square r0 over capital K. I am just going to call this lambda to make my subsequent equations shorter to write. The interpretation of this quantity is also not quite difficult. This is mu v0 square over k over r0. Now mu v0 square is double the kinetic energy of the satellite. Note that for the satellite, as we have said before, mass and reduced mass are almost identical. And the denominator k by r0 is nothing but the magnitude of the potential energy. So this lambda is essentially related to the ratio of the kinetic energy to the potential energy of the satellite at the initial point. Now, in terms of this lambda, all of these expressions can be rewritten in a rather compact fashion. Small r0 simply works out to be capital lambda r0 cosine square beta 0. E sine theta 0 is lambda cosine beta 0 sine beta 0, and E cosine theta 0 is simply lambda times cos square beta 0 minus 1. Now, these expressions immediately suggest a way ahead for the solution. Remember, for the solution, we need to figure out r0, small r0 that is, E and theta 0. Small r0 is already given here. Lambda is a quantity that we can calculate from the initial conditions and the other parameters like capital K and mu, describing the interaction and the mass of the object. R0 is very much part of our initial measurement. Beta 0 is also part of our initial measurement. So small r0 is already known. Here we see that E sin theta 0 and E cos theta 0 are both given in terms of our initial measurements. Now, solving them for theta 0 and E separately is of course pretty easy. All you do is divide these two expressions to get tan theta 0 equals the ratio of these two quantities, and after you divide through by lambda cos square beta 0, you end up with tan beta 0 divided by 1 minus sec square beta 0 over lambda. So that's tan theta 0. From that you can find out exactly where the perigee is located. To find E, all you have to do is square and add these two expressions. And when you square and add these two, you get lambda square cos square beta 0 sin square beta 0 plus lambda square cos to the 4 beta 0. The sum of these two giving me this. You also get a minus twice lambda cos square beta 0 term from here and a plus 1. And you can collect them all together. With cos square beta 0, getting lambda square minus 2 lambda as a prefactor, which can be rewritten of course as lambda minus 1 whole square. But that will require us to add an extra cos square beta 0, which has to be taken away from the 1, and that gives you a sin square beta 0. So this and this completes the solution of our problem. Determination of the orbit from the values that you can observe about the satellite right after the rocket has burned out. Let us now take a look at two special consequences of this formula for the eccentricity that we have derived here. We know that for an unbounded orbit, that is for a parabola or a hyperbola, E has to be bigger than 1. or at least equal to 1. Now using that, we can easily figure out that if you want to have an unbounded orbit, you must have e square minus 1 being positive, which means this thing has to be positive, which boils down to lambda into lambda minus 2 cosine square beta 0 being greater than or equal to 0. Now cosine square beta 0 is always positive, so this boils down to the factor lambda into lambda minus 2 being greater than or equal to 0. There are now two possibilities. Either lambda is negative, less than or equal to 0, in which case lambda minus 2 will also be negative, so the product of two negative factors would give you a negative value, or lambda has to be bigger than or equal to 2. We will talk about lambda being negative soon, but let's focus on lambda being greater than or equal to 2 here. Now, if you use the value for lambda that we have, this tells us that mu v0 square r0 over k, our capital lambda, is greater than or equal to 2, and this gives us the velocity that you need for an unbounded orbit to be bigger than or equal to this value, the so-called escape velocity from the Earth. It turns out to be over twice k over mu r0. R0, remember, is not necessarily the radius of the Earth, but the distance from the center of the Earth to the point where the satellite went into free gravitational motion. That is, where the rockets have stopped burning. Now, replacing the k by g m Earth times mass of satellite, and realizing that mu for the Earth satellite system is almost exactly equal to the mass of the satellite, gives us a very familiar formula for the escape velocity, root over 2g me by r0, where r0 can be taken to be the radius of the Earth if you're talking of projection from the surface of the Earth itself, and typically this would be the distance from the center of the Earth where the particle has been released after the rockets have stopped burning. Now, one important feature of this result is, of course, that it does not depend on the angle of projection. It depends only on the mass of the central object, in this case the Earth, and the distance from the central object of the point of projection. Now, this is easy enough to understand if you remember that we had already shown before that for a Kepler potential, you get unbounded orbits whenever the energy is positive, and the energy does not really depend on the direction in which the satellite is moving. Indeed, using energy considerations, this result could have been figured out in a much quicker fashion by simply using the fact that the potential energy at a distance capital R0 is given by this. The kinetic energy would be half mu v0 square, and for this to be greater than or equal to 0, which is what you need for unbounded orbits, would immediately give you this result for v0. That is the reason why there is no mention of the angle in here. Let us now return to the other case of lambda being less than 0. Note that lambda is this quantity. For this to be negative, you have to have a negative value for the constant k. This is the case that will always occur regardless of the value of v0 if the force, instead of being attractive, is actually repulsive. This result now shows that if you have a repulsive inverse square force, the orbit will always be a hyperbola because lambda will always be less than 0. Let me now talk about another case which we just ignored a while ago when talking about this. E square could also be exactly equal to 1, that is, this would have been exactly equal to 0 if cos square beta 0 is 0. This means that beta 0 could be either pi by 2 or minus pi by 2. Let us try to understand what we are saying here. Remember that this is the distance r0 from the center of the Earth to the point where our initial condition is given. Beta 0 is an angle measured from the cross-radial direction. So beta 0 being plus or minus pi by 2 actually means that the particle is being shot right at the center of the Earth or directly away from the center of the Earth. In both cases, we know that the particle would ultimately travel in a straight line until it crashes to the Earth. Of course, if the velocity here was too big, it would keep on going forever without ever coming to a halt. But note that in all these cases, E is exactly equal to 1, and what we have, or what we should have, from the theory of conic sections is that this should be actually a parabola. But if you think about it, a parabolic orbit round the Earth would have looked something like this. And then, if it became narrower and narrower, you would essentially have a parabolic orbit, or rather half of a parabolic orbit, which is now almost exactly a straight line, and in the limit it becomes a straight line directed right at the center of the Earth. Note that while it is a straight line, it's really not a complete straight line, it's just half a line segment. The motion stops when it hits the Earth. In fact, it doesn't even have to hit the center of the Earth. The moment it hits the surface of the Earth, this kind of motion has stopped there. But that is a special case which this equation also talks about. Let us now talk about a special case of our results. Remember, we had found out that small r0, theta 0 and E, the quantities that describe my orbit, can be written down exactly in terms of the parameters lambda, capital R0 and beta 0, where of course lambda is a number which is directly related to the speed of projection along with the other factors here. Now the special case that I'm going to talk about now is a case where beta 0 is 0. Let me remind you once again that this means that the particle or the satellite is being projected at right angles to the line of sight from the center of the Earth. Now in this special case, our equations become very, very simple. Tan theta 0 becomes 0, which means theta 0 is either 0 or pi. E here for beta 0 equal to 0 simply becomes square root of lambda minus 1 whole square, and that means that E, since it's a positive number, has to be the modulus of lambda minus 1, and small r0 from the formula that we have simply ends up with capital lambda times r0. Now let us try to understand the two cases that we are seeing here. Whether E will be lambda minus 1 or 1 minus lambda will of course depend on how big lambda is. Lambda, remember, is this quantity. So if the velocity or speed or projection is too big, then what you have is a lambda which can be bigger than 1. And so in that case, for large V, E is actually lambda minus 1, and therefore lambda works to be 1 plus E, and r0, the distance of projection, is small r0 over 1 plus E. Now this happens to be the minimum distance or the perigee distance for the satellite, and this is pretty easy to understand. Remember, during the orbit, if it's an elliptical orbit, the velocity is perpendicular to the radius vector at precisely 2 points, the perigee and the apogee. The velocity of the particle is largest at the perigee and smallest at the apogee. So in this case, if V0 is large, the point of projection actually happens to be the perigee of the orbit. On the other hand, if the velocity is smaller, so that lambda is less than 1, then E would be 1 minus lambda, and capital R0, the distance to projection, would be small r0 over 1 minus E. This actually is R max. That is, the apogee distance. Small velocities correspond to apogee distances, whereas large velocities correspond to a perigee distance. This may sound a bit counterintuitive at first, but remember, what this really says is that if your velocity is too small, then it will approach closer to the Earth on the other half of the orbit than the distance from which you projected it. If you look at it that way, this result of course makes perfect sense. The two possible values for theta 0 are also easy to understand. If V0 is large, that is, our point of projection is the perigee, then theta 0 of course is 0. Theta 0, remember, is measured from the line joining the center of the Earth to the perigee. On the other hand, if velocity is small so that the point of projection is actually the apogee, we will get theta 0 equals pi. The perigee would then be on the opposite side of the Earth. In what is left of this lecture, we will take a quick look at a topic which has been very much in the news of late. What with the successful launches of India's Chandrayaan or the Aditya L1 missions. This is the issue of orbit transfer. Changing the orbit of a satellite from one particular orbit to another different orbit. Now, this is a huge topic and many different kinds of changes of orbit can take place. We will briefly mention only the most commonly studied one, the one which is also most fuel efficient, and this is called the Hofmann transfer. Now, one point that we have to bear in mind in this case is that during any such orbit transfer, the velocity has to change either its magnitude or its direction or both during a brief period. We are only talking about impulsive transfers at this stage, where, as we mentioned before, the velocity of the satellite is changed by a large thrust without considering any change in the position of the orbit. Now, when such changes take place, the satellite, of course, has to fire its rockets and burn a lot of fuel. According to the standard rocket equations, which we have learned when we study motion of variable mass systems, the mass of the fuel that has to be burnt is exponentially dependent on the change in speed of the particle. The larger the change in speed of the satellite, the more the amount of fuel you have to burn. Of course, if you have to burn more fuel, you have to carry more fuel with you to begin with, which, given the limited amount of mass a satellite can only accommodate, limits the amount of equipment or people it can carry. Keeping this in mind, it would be nice to be able to design a transfer protocol where the change in velocity, or rather the magnitude of the change in velocity, is kept as small as possible. And this is where the Hofmann transfer protocol really shines. Note that if the transfer requires a change in direction of the velocity, then there will be a change even if the magnitude of the velocity, that is the speed, remains the same. The smallest magnitude for the change of velocity would actually occur if the change is in the same direction as the initial velocity. And that is exactly what the Hofmann transfer achieves. Now, in order to describe this, we are going to consider a situation where a satellite is being transferred from a circular orbit, the blue one with radius RA, which it already is in, to the larger red one with radius RB. In order to do that, what you would do at the point P is fire the rockets in a satellite to speed it up so that it then travels in an elliptical path. We will choose the semi-major axis of the ellipse so that it exactly lands up at the point Q on the other circle. That is, the semi-major axis would have to be RA plus RB over 2. And once it is at the point Q, the apogee of this elliptical orbit, what we are going to do is turn on the thrusters once again, speed up the particle or the satellite so that it now executes a circular orbit which is given by the red one. So although we have drawn the full transfer ellipse in green here, what actually takes place is that the particle travels only in half of the elliptical path. So it was traveling in this circular path to begin with. At P, the rockets are fired, it speeds up, it travels in an elliptical path, reaches Q, where the rockets are fired once again, which prevents it from returning back to the point P along this lower half of the green path, but rather sends it into this circular orbit here. Let us now quickly calculate the change in speed, the net change that happens at the points P and Q during a Hofmann transfer. Note that at the point P, the particle in the blue orbit, the circular orbit, was already moving in a direction which is tangential to the circle, and because P is the perigee of the transfer orbit, in the transfer orbit 2, the satellite will be moving in the same direction. So all you need to do to find the change in velocity is subtract the two speeds. The same goes for the point Q. Now, at the point P, the velocity of the satellite in its transfer orbit, the final velocity that it acquires at the point P after the impulse, is given by a formula that we had derived earlier, root over 2k by mu by Ra plus Rb into Rb by Ra. Here Ra and Rb, in addition to being the radii of the two circles, are also the perigee and the apogee distances for the Hofmann transfer orbit. That's what we have used here. Of course, the velocity of the satellite before the impulse was given, the initial velocity at this point P, was simply root over k by mu Ra. And so if you subtract the two, you get delta Vp, the change in the velocity at the point P. If you take root over k by mu Ra as a common factor out, you get this expression, root over k by mu Ra into square root of twice Rb by Ra plus Rb minus 1. Now a very similar thing happens again at the point Q, where the initial velocity at the point Q, the velocity before the rocket is turned on, is actually the apogee velocity of the transfer orbit, root over 2k by mu Ra plus Rb multiplied by a factor of Ra by Rb. The velocity after the impulse has to be the velocity in the red circular orbit, and that's given by root over k by mu Rb. So this is what delta Vq works out to be. If you add the two together, you get the net change in velocity during a Hofmann transfer. And you can simplify the expression a bit by dragging out a factor of root over k by mu Ra times Rb. And this makes the whole thing looks a bit like this. This looks a bit complicated, but it's nothing but the sum of these two expressions. And if you use Rb by Ra, this ratio, which we are going to call rho, as a parameter, what you get is this final result, root over k by mu Rb, the speed in the final orbit, times this factor which depends on rho. You can convince yourselves that this increases as rho increases. That's sort of obvious, although the algebra may be a bit complicated here. Now, to get an idea about the kind of changes in speed we are talking about, if rho is 4, that is, the circular orbit is 4 times larger in radius than the initial orbit, what we get from this formula is delta Vp plus delta Vq works out to be 3 times, that is root over 4 plus 1, times root over 2 by 5 minus 1, multiplied by this root over k by mu Rb, and that's 90% of the speed in the outer orbit. So this is the amount by which the speed will have to be changed in the two impulses during an Hofmann transfer. Of course, if rho is much larger, the change in speed would also have to be larger. Indeed, if the outer orbit is large enough, then the change in speed required would be larger than the speed in the outer orbit. Note that so far we have talked about Hofmann transfer being between two circular orbits of different radii. However, the same idea can be used very easily to transfer a satellite from a smaller elliptical orbit to a larger elliptical orbit as long as their axes coincide. In which case, we will turn the thrusters on when the satellite is at the perigee of the smaller orbit, putting it into a Hofmann transfer orbit whose perigee happens to be the same point as this one, but its apogee is at the apogee of the other orbit, and when it reaches that point, you will start the rockets once again to speed it up so that it now goes into the outer larger orbit. By the way, the same basic idea can also be used to transfer the satellite in the other direction. Slowing down the satellite at the apogee of the larger orbit so that it goes into a Hofmann transfer orbit, and then slowing it down once again when it reaches its perigee to put it in the smaller orbit. Note that speeding up a satellite and slowing it down both requires the expenditure of a lot of fuel. So in both situations, the Hofmann transfer orbit, because it changes the speed by the smallest amount, is to be preferred as long as you're transferring between coaxial orbits. Of course, sometimes, depending on your situation, you may want to transfer to other orbits. That will involve other maneuvers which are more complicated. Now, describing all these other maneuvers would actually require a whole course in itself. And I am not really an expert in astrodynamics, so I would not be the correct person to learn all of these things from. You can, of course, pick up further details on courses available on the net or from other textbooks. I do want to mention one special kind of more complex maneuver than the Hofmann transfer, for the simple reason that it takes care of an issue that we raised a while ago. Note that we said that if the radii of the two orbits, the initial one and the final one, differ by a very large amount, then the amount of fuel that needs to be burned for the Hofmann transfer would be quite large, because the two changes in velocities at the perigee of the Hofmann orbit and the apogee of the Hofmann orbit would end up being quite a huge amount. In such situations, more complicated maneuvers might actually lead to a reduction in the amount of energy required. One example is the usage of something called a bi-elliptic Hofmann transfer. Here, you do an impulsive change of orbit, say for a particle moving in this small circular orbit, of course small in this scale. You would turn the thrusters on at this point and put the particle in a larger Hofmann-like orbit, but this time the apogee of that Hofmann orbit is not at the target radius, but it's actually quite further away. Then you apply a further boost to send it into a larger elliptical Hofmann-like orbit, which ultimately has its apogee on the circular orbit, the larger circular orbit. And of course, once you reach this point, you once again have to use the thrusters in order to send the particle or satellite in this larger orbit. The important point is, once the two radii involved, that of the outer and the inner circular orbit, differ by a large enough fraction, the bi-elliptic transfer method, so called because you're doing it via two elliptical Hofmann-like orbits, turns out to actually require less fuel than the two-impulse Hofmann transfer. So this three-impulse bi-elliptic transfer may be more efficient. There is a downside though. It's obvious that for the bi-elliptic transfer, the satellite would have to first traverse this large half-elliptical orbit and then go through another large half-elliptical orbit. And both of these would take quite a lot of time. The time taken can be easily calculated by using the time period formula, except that you need to put in an extra factor of half, because you're actually traversing only half of the orbit. That being said, the half time period of this orbit added to the half time period of this orbit may be quite large compared to the time period, or rather the half time period of a single Hofmann transfer orbit. The Hofmann transfer would definitely win in time, while it may lose out in fuel in a special situation. So depending on various factors, you may or may not opt for a bi-elliptic transfer, even though it may lead to a smaller fuel consumption, because time may also be of essence. Of course, if time were really of the essence, like when you were trying to put men into the moon, you would actually not really depend so much on gravitational transfer from one point to another, but keep the rockets on for a much longer period of time, ensuring that the overall time taken is reduced. This of course explains why the Apollo 11 mission took a much shorter time to get to the moon than did the Chandrayaan 40 years later. The reason, of course, is simple. For the Apollo missions, sending a man to the moon in as short a time as possible was a priority, because you had to ensure that the astronauts had enough food and other provisions to last the entire journey and back. Whereas for the instruments that have been sent to the moon using the Chandrayaan satellite, time was really not that critical a thing. Let me just end this talk by giving you a very brief description of the kind of orbit the Chandrayaan used to get into the moon. You will see that some of the ideas that we have talked about here were actually employed rather cleverly to ensure that you actually manage to reach the moon and end up successfully landing a module there. Note though that the problem of transferring a satellite from one orbit to another is a relatively simple problem. Rendezvousing with another celestial object, in this case the moon, is a much more different ball game, because you have to ensure that by the time your satellite gets to the other orbit, the moon is really there. That in itself is a non-trivial thing to do. Let me now give you a quick description of the Chandrayaan's orbit based on a tweet that ISRO itself had put out. Chandrayaan was launched in its orbit using the Launch Vehicle Mark III, LVM-3. LVM-3 has been used in the past and is typically designed for putting satellites in geostationary or near geostationary orbit. But in this case, the orbit that was used is quite different. You can see that the initial orbit essentially is this one. And then, once it's at its perigee once again, its velocity was boosted up so that it went into a larger orbit with the same, or at least roughly the same perigee, but an apogee distance which is larger. This procedure was carried out once again and again and again, at least 5 times. And then when the time was right, remember, you have to ensure that the moon would be in its right position by the time the lunar transfer trajectory, which is effectively a Hofmann-like trajectory, carried your satellite to the moon's position. Now, somewhere in this vicinity, the problem becomes more complicated, because here the satellite is actually under an attraction of both the Earth and the moon, and it's really a 3-body problem which is much more complicated. But quite soon, the satellite enters a region where it's basically moon's gravity which dominates, and after that it goes into a lunar insertion orbit, a large orbit like this, with a perigee pretty close to the surface of the moon, but an apogee very far away. But now once it comes back to the perigee, or rather, the word is not perigee any longer. I'm not very sure what the word really should be. It's actually perilunar point. I don't know whether that is the term which is used, but let's call it perilunar anyway. At the perilune, the velocity of the satellite is now slowed down by using retro rockets. So it now goes into a slightly smaller orbit, same perilune, closer apolune, and this is done several times until it reaches a very circular orbit around the moon, from which point the lander was sent down to finally meet the lunar surface and land there safely. Now, as I said, the real reason behind this whole procedure was to ensure that a very small amount of fuel was needed, and the timing was just right. By the time the Chandrayaan got to the lunar trajectory, the moon was really there to capture it. And you can of course find much more details about this from the ISRO website if you are interested. In the next lecture, we are going to take a look at a different class of orbits for the Kepler potential, the hyperbolic orbits. And we will also see how they are important for scattering problems and derive the celebrated Rutherford scattering formula. Bye till then.